position as a function of time for a particle, but turns out it was going, he didn't know it, but it was going to be. So anyway, which evolves according to an equation called the Schrödinger equation. The wave function psi depends on both space and time. Schrödinger's equation describes waves that fluctuate in both space and time. So how does the particle behavior come in? The answer is that the quantum wave function does not describe something like an electromagnetic wave, which one thinks of as a physical thing existing at a point in space and fluctuating in time. The quantum wave function describes a probability wave. So this is what I mean. When Schrödinger first wrote down the wave equation for matter, he thought he was writing down the wave equation for matter, and it's sort of like this, like what are they even trying to do in quantum mechanics, right? Like quantum mechanics itself has the clue. Mechanics generally means something as simple as writing down the position of something as a function of time, for example, or even a function of space. You could write down, say, an equation for the moon as a function of time. Now, if you write it down as a classical mechanics equation, in fact, those are written down, right? The equations of motion, the laws of motion, gravitation, etc. Just Newtonian mechanics can give you the function or the equation of the moon's position as a function of time. And what is more, we actually can write that down and get the answer like 1,000 years from now. Like it just works, right? So similar thing in quantum mechanics. Ultimately, they want to write down some equation which gives the position, for example, of a particle as a function of time and also space, turns out. So it's not like they're trying to do something super different or novel. The novelty is that now we're operating at a very small scale. We're operating at the scale of particles or subatomic scales and things that are very tiny, teeny tiny, okay? And the teeny tininess brings into the domain certain extra other things, certain extra features, such as the uncertainty principle turns out, and such as this probabilistic nature, which people were not used to. Because turns out that the Schrödinger wave equation is actually a probabilistic type of a thing. It actually gives you the probability of finding that particle at some point, not the deterministic answer for the position of that particle as a function of time and space. It's the probability of finding that particle, or it's the probability of finding an electron, okay? So in quantum mechanics, we deal in probabilities. We cannot know for sure, like with certainty, we cannot write things down, okay? And so even some of the contributors of quantum mechanics did not pick up on this until later, and it came as a shock even to them. Schrödinger himself was not happy when he found out that the wave equation that he had written down was ultimately a probabilistic object, if you will. So how does the particle behavior come in? The answer is that the quantum wave function does not describe something like an electromagnetic wave, which one thinks of as a physical thing existing at a point in space and fluctuating in time. The quantum wave function describes a probability wave. A probability wave. Quantum theory asserts that the wave function is all one can know about the system. One cannot predict with certainty exactly where the particle will be at a given time, just the probability. Isn't that so interesting though? Isn't that so very, very interesting? It is just the probability. And the shock at that point was that people were not used to that. People were used to getting deterministic answers. If there was an equation written down for something, like the moon, for example, which is a classical object, or say you or me or trees or cats or cars, people expected a deterministic answer. People did not expect, oh, you'll just give me the probability of something happening as an answer. That is not acceptable. People were not very happy about that, okay? The classical physicists. So you can start to see how there was this divide between the classical physicists and the quantum physics, okay, or the quantum physicists. and